Good morning, everyone. We're going to play again a little bit with the chopsticks one more time. Please don't break them yet. You can break them later. You guys are 5 over here. Can you please pass 2 over there? Yeah, I'll get the extra one. Oh, you have 3 there? 4? Just give me 1. Just pass those 2. Here you guys are 4, and here you have 1 more. Okay, we're going to play a little bit more with the chopsticks in order to understand what are the fracture modes. In case you need additional chopsticks, feel free to grab one. The last thing that we saw was that we could calculate a stress intensity factor at the, please grab some chopsticks. The chopsticks are over there. We're going to play with chopsticks, so feel free to grab some chopsticks. And as I was saying, we calculated the stress intensity factor at the tip of a fracture, and that was defined as the product of a distance times stress. And when you take a limit of that product and you approach to the tip, it happens that those two, instead of going to this one, instead of going to 0, well, this one goes to 0, this one goes to negative infinity, but when you take the product, some terms cancel out, and then you end up with a finite number that tells you what is the intensity at the tip. And that's, as we say, is proportional to the pressure in the fracture and also the square root of the length of the fracture. So longer fractures, for the same pressure, we have a higher stress intensity. Okay, what I wanted to discuss now is what is this number 1 in Roman numbers. And that's related to something that we call fracture modes. And the first fracture mode that we have seen is mode number 1. In mode number 1, we have a fracture. Well, let me do it the other direction so it's consistent with my other drawings. In mode number 1, we propagate a fracture by pulling apart a solid. And the faces of the solid go in opposite directions so that here at the tip, we have a very clear state of tension. So if you use the chopsticks, then mode number 1 would be the one in which you pull apart the two tips of the chopstick, and so that parallel to each other it opens up. That's mode number 1. But that's not the only one. There are 3. This is the one that we use for a hydraulic fracture that has pressure inside. The pressure moves the two walls apart, and that gives origin to mode number 1. But we also have mode number 2 and mode number 3. Mode number 1 is called open mode. Mode number 2 is called shear in plane. And instead of having the faces of the material to go in opposite directions, in this case, what we do is, if we have a fracture, push in one direction, you pull in the other one. And with the chopsticks, that will be pulling on one end, or let me push as in the figure, push the top one and pull the second one, the bottom one. And you can try to do this, but it's going to be very hard to break the chopsticks like that. Mode number 1, it gives you stress intensity factor 1. Mode number 2, it gives you stress intensity factor number 2. And the last one is mode number 3, which is shear but out of plane. And in this case, this is called K3, and it looks something like this. Let me try to draw this. It's a little bit more difficult than the other ones. Something like this, where here we apply a shear, one all right. This is important to know from a fundamental point of view to get to know how rocks fail. Actually, when, for example, you load a rock, or as we saw when we load a wellbore, but let's just think now of a rock and has a pore inside. Start to fail because of stress concentration favor so also at the micro scale of rocks, these type of fracture modes are important. And here I have another example. This is what we just saw. For example, when you have fractures or rock defects inside the rock and you start to load it, always fractures are going to concentrate stress at the tip, and fractures are going to start to grow at the locations of the tip. And it could be sometimes in open mode, but some other times in shear mode. Well, a very interesting case is that it has been recently seen that, for example, in the field, hydraulic fractures do not really look like what we commonly assume, just a single plane. When you go to the field, many times what we have seen lately is that fractures look a lot more complicated than what we think in our models. I know the hand. I don't know if you recognize it. And as you can see in this example, there are several fractures, one here, one there, another there. Presumably, a few of these are hydraulic fractures. And being so close, we're going to see later on, it's very difficult for several reasons. Because fractures interact with each other. When you open one fracture, it's very difficult to open another one. But what has been recently proposed, and it makes a lot of sense, is also observed in nature, is that part of the complexity of these fractures is related to having, where is that? Here. To having mode 3 and mode 2 combinations with hydraulic fractures. So let me explain what that means. When we just have a pure mode 1 fracture, if you have an initial fracture where this is a tip and now 3 dimensions, and you just have mode 1, you would expect this fracture to continue opening in the same plane of the fracture. And it would just propagate in that plane. Why? Because you just have that tensile stress in that plane. If you have an initial fracture that looks something like this, and now you have a shear at the tip, your fracture would tend to curve. Will go in another direction. So it can twist because of the shear that you apply in this direction. And last, if you have an initial open mode fracture, but when it gets to the tip, now it finds a shear which is in this direction, the fracture would tend to what is called, is going to tend to segment. And instead of being one plane, it's going to segment into several planes. And those are going to continue opening in a combination of mode 1 and mode 3. And again, the angle will depend on how strong those shear stresses are. But if there is just a little bit of shear stress, then they are going to rotate a little bit. And when you have these now several fractures propagating at the same time, then instead of just having one, then you're going to have many. And these, together with natural fractures, presumably are also part of what causes a lot of hydraulic fracture complexity that we observe in the field, different to the usually assumed just single planar fracture. All right. Let's see where we are. So mode 1, mode 2, mode 3. We already talked about that. Let's come back to mode 1. The stress intensity factor, as we call it, is Ki, but remember that these stresses at the tip of a fracture in open mode. In order to know if a fracture propagates or not, we need to compare this to the critical stress intensity factor, also fracture toughness. And this is the fracture toughness in mode 1, but also similarly you're going to have fracture toughness in mode 2 and in mode 3. And remember that the fracture toughness is going to be a property of the material, and the stress intensity factor is going to be a variable. But for example, the length of your fracture on the pressure that you apply, this one is a property of the material. And since it's a property, we measure it in the laboratory. And usually the method that we use to measure this is called, it's very popular in rocks. It's called semicircular bending test. And the semicircular bending test, what it does is it measures fracture toughness on a semi-cylindrical piece of rock by creating a flaw in the rock or small fracture. This small fracture or small notch is going to have a height A. The rock is going to have a radius R, and you apply on the top, similar to the Brazilian test, but now it's with the semicircular sample. And on the Brazilian test, we didn't have to worry about this, but in this case, you have to use some rollers here on the bottom so that when you apply the pressure, the rock can go sideways without any problem. So these are rollers. And here you're going to have the reaction to the applied stress. What is going to be the reaction? If this is P, if this is well centered, the reaction has to be P over 2. All right, let me see what I am forgetting. As you may notice here, it's very important that here we quantify what is the distance between here and there, because the bigger the distance, the higher the stress I'm going to create here, and also the bigger the notch, the higher the stress I'm going to create. So that's going to be the variable S. And the last one, it's similar to the Brazilian test. I'm going to have a given rock thickness. So this is going to be something like this. And where these are the rollers. And we can measure the stress intensity. K1C is going to be equal to the maximum pressure proportional to the distance of the notch. So that's going to be part of the intensity. It's proportional to the radius of the sample to inversion in proportion to the radius of the sample, the length, and times a geometric factor, which is a function of A, S, and R, and it's about 5 when S divided by R is equal to 0.8, if I remember correctly. But you know, it's just an equation. You don't have to memorize this equation. The only thing I want you to remember is that there is a test that can measure fracture toughness, and it is this semicircular bending test. And I have an example over here of a rock that we failed in class last time. Unfortunately now, we don't have the time to do that. So this is what the rock looks like. So for example, this is a limestone, and there you see the notch. When you apply a load from the top, it breaks like that, and that's an open mode fracture. And you can observe that it propagates as you would expect, following the notch and following that plane. And the plane is not always perfectly plane with rocks. It's not perfectly planar, and it has some tortuosity. If you had mode number 2, for example, the fracture would be like that, and probably the fracture would turn. And if it was number 3, then you have this displacement, and also the fracture plane may turn in this direction. But since this is number 1, it just follows the plane of the notch. Okay. Something else that I like that you remember is that we have typical values of fracture toughness, and they go all the way from 0 for materials that are not cemented to more or less about 2 MPa per meter square root. This is a very uncommon unit, but these are the units of intensity. pressure times square root of distance. All right, so just to have an idea about what these values are, let's solve a problem. And this is problem 7.1, if I remember correctly. Let me find it. Okay, here. Let's work quickly on this. We have a fracture that has a length of 10 meters. Actually, it's a half length of 10 meters. So this is 10 meters. This is 10 meters. It has a pressure inside of constant along the fracture of 20.5 MPa. And in the far field, the minimum total stress is 20 MPa. And we have the properties of the rock. It's relatively a soft rock, 1 gigapascal of Young modulus and Poisson ratio of 0.25. I like that you tell me for this rock what is the maximum width and stress intensity at the tip. So what is the width and what is Ki at the tip? Yeah, I'm going to move this down to the left. Okay. Can you guys work on this quickly? Probably I can give some extra points to whoever solves the problem without looking at the solution, of course. So what you need are the equations of stress intensity and also the equation for the width. But pay attention to the problem, okay? There is a trick there. You need to consider the fracture, but also what is outside the fracture. Are there any questions so far? Okay, what do you want? What do you have, Mr. Ms. Tafoya? Sorry.
I got the width as being 3.6 times 10 to the negative 7.
3.6 times 10 to the negative 7 meters. Be careful with the units. But first of all, what do you have to do first? You need to calculate the net pressure, because all these equations that we have been using use net pressure. So the first thing that you have to do is to calculate the net pressure, which in this case is going to be how much? It's going to be 0.5 MPa, because it's the difference between the pressure inside the fracture and the pressure outside. And then the width is going to be 4 times pressure times fracture half length divided by the plane strain Young modulus. Right? If I remember correctly, that's the equation. And probably here we can also calculate what is a plane strain Young modulus. I'm sorry, the plane strain modulus, not plane strain Young modulus, just plane strain modulus. Anyone calculated that one? If you remember, plane strain Young modulus is, I don't know why I say plane strain Young modulus. Plane strain modulus is the Young modulus divided 1 minus Poisson ratio square. Okay, 1.07 gigapascal. All right, so be careful with the units now, because your pressure here is megapascals and your plane strain modulus is in gigapascals. So, Mr. Foya, was the number was using the correct units or not? No. Okay, so this should be 0.5 MPa times 10 meters divided 1070 MPa. Cancel that one with that one. And that will be equal to that's about 4 to 10 to the minus 3, right? Did anyone calculate the actual number? Zero. Oh, because, okay, yeah. Because I didn't see this 0.5. So then what's the number? 0.019 meter. Okay. All right, so then that number, it is about 2 centimeters, and 2 centimeters, it's more or less, a little bit less than 1 inch. So just very rough, we could say, is about 1 inch. That's the width of the fracture. But something that I like that you remember is not the specific numbers, but you consider that what we are dividing. And here we're dividing usually an amount which is in the order of MPAs divided 1,000 MPa. So the width of the fracture is always in a relationship of more or less 1,000th of the value that you multiply for. So this one times that one is going to be 1,000th of the length. So if you have a fracture length of, let me think about, I don't know, 100 feet, then this is going to be divided by more or less 1,000. That's going to be the width of the fracture. So the slenderness of the fracture is more or less 1,000 for rocks. If the length is 1,000, the width is going to be 1. So they are very, very slender. These fractures are very thin. And if you think about this in terms of PSI, also the typical net pressures that we have in fractures are in the order of 100 to maximum 1,000 PSI. And usually here in the denominator, we have 1,000,000 PSI or something like that. So when you take the ratio, also it goes to 1,000 or even a little bit less. So the fractures are very thin compared to the length. They are very slender. And what about the stress intensity factor? If I remember correctly, the question of this is going to be like that. Let me double check. Probably I have here the solution. And okay, so when you plug the numbers, what do you guys get? Probably we see a solution already here. 2.8 MPa times meter square root. And do you remember what I told you the typical values of fracture toughness? About 2, and most rocks they will have even less. A very tough rock will have 2, but rocks which are not that strong will have, for example, this limestone over here, we measured it in class last time, and the value was 0.4 MPa meter squared. So this is a lot higher than that. And you can see that already for a fracture which is about 10 meters half length or 30 feet half length, with a pressure which is relatively small, which is 0.5 MPa or 70 PSI, already the intensity is quite high. And the message of this part of the problem is that as the fracture starts to grow, usually when it has already some length, the fracture intensity is going to be always higher than the toughness. So after the fracture starts to grow a little bit, we actually don't care anymore about toughness, because always the intensity is going to be higher than the toughness. And the fracture is just going to grow without any control on the rock. Toughness is not going to control the growth of the fracture. There are other things that are going to control the growth of the fracture. Like, for example, the viscosity of the fluid or how much fluid gets into the rock. So part of this fracture propagation and how it propagates is very important to know. Toughness, intensity, it's important to know. But after the fracture develops some length, it doesn't matter anymore what is the toughness of the fracture. And that's why in the models we're going to see now, not consider that. And let me move this over here to have a little more of a space. And we'll start talking about the hydraulic fracturing, single hydraulic fracture models, single and planar hydraulic fracture models. Okay. These models that we're going to see now, they are very basic, but they contain almost everything what we need in order to understand a modern hydraulic fracture simulator. So please pay attention to all what we're going to see, but again, as I tell, they are very simple because they consider just one fracture, and also that this fracture it goes just into a plane. Okay, so let me divide this in 3. And we'll start talking about these models. The first model is called the Kgd model. And this model, don't worry about the initial. These are the initials or last names of people. And that's not important right now. What is important is to understand what they do. And the first one considers a fracture that has a shape, a cross section, which is like an ellipse. It has a constant height. HF, that we will assume that we know right now, and we'll see how to determine that later on. And as you get to the tip, of course, the width of the fracture is going to get smaller and smaller. But this is just a series of ellipses. It looks like you may think of this as a planar wing of a plane. And the width is going to be variable at the wellbore, and it's going to vary also as a function of the distance from the wellbore to the tip of the fracture. The fracture half length, here I'm just drawing one wing of the fracture, but this is going to be 2 wings, and this is going to be the half length of the fracture. And what this model applies is, hopefully you will remember when we talk about this, it assumes that if you take a cross section of the fracture, that's subjected to something that we call plane strain. So this fracture that we have over here, in that cross section, is the same as this one over here. So this fracture is that one. And notice that it's not growing up and down, so those are the tips of the fracture, and that shape varies along the distance. All right. What is important about this model? It is important that this Kgd model usually is used for long fractures. Where the fracture half length is higher than the fracture height. Once you assume this geometry, it's relatively simple to show how much fluid can flow through the fracture and what is the gradient that you need for that, the pressure gradient. And when you put together the equations of pressure gradient, how much flow goes into the fracture, what is the aperture that you need to open the fracture, and also if you consider leak-off, you're going to be able to predict what is the fracture length, what is the net pressure at the fracture of the fracture, and also what is the width as a function of time. And one thing that we have to do in order to get these equations is we need to assume an injection rate. And for this case, usually hydraulic fractures are done with a more or less constant injection rate, and that's what we're going to use here. We're going to assume a constant injection rate, which is we're going to call I as a function of time, and that's going to be a constant. And also we'll assume no leak off. And once you put all of these assumptions together, you can predict again what are all of these as a function of time. I'm just going to write one of the equations because they're kind of long, and I have them in my notes, so there's no need to copy all of those again. But I just want to emphasize here what all the variables do. Okay, that's the equation. The equation tells you that the fracture half length is proportional to time, which makes sense. And it's proportional to the injection rate, which also makes sense. The more you inject, the higher the fracture length is going to be. It's inversely proportional to viscosity. That makes sense too, because the higher the viscosity, the harder it's going to be for that fracture to propagate. That actually shows up a lot more in the net pressure. We're going to see the equation in a bit. And it is inversely proportional to the fracture height, because the taller the fracture, the more fluid you need in order to inject, in order to fill up that volume and to have the fracture to extend. So the only thing I'm going to do here is here to put the coefficients. Net pressure is going to be also proportional to time, and the width is going to be proportional to time. And let's look at the equations over here. Okay, here you have a more or less prettier description of these models. We're going to see in a bit the Kgd and the Radial Model, but these are the equations. Fracture half length, as I was telling you, is proportional to the, there was a mistake in my notes, I'll correct it just in a bit, but it's proportional to the 4/5 of the time. The width at the wellbore, again, is proportional to time, inversely proportional to the stiffness of the rock, which means the stiffer the rock, the harder it's going to be to open a fracture. And the net pressure, as it makes sense too, is proportional to viscosity. The more viscous the fluid you inject, the higher the net pressure is going to be. So with these equations, at the end of the day, what we want to do is we want to design a fracture. That's the ultimate objective of what we want to do. We want to design what is the fracture, length, what is the fracture width, and what is the fracture height, which sometimes is a little bit outside our control. But we're going to see later on that depending on net pressure, we can change that. So I was telling you that this one is 4/5, and this one is 1/5 and 1/5. All right. I have an assignment that in which you have to use these equations in order to predict fracture length, net pressure, and width, and then after you do that, you will see that it's very easy. But now what we're going to do is we're going to talk a little bit more about the other models. So again, the equations, you can look at those in my notes. Let's talk about the following model. It's called the Kgd model. And again, those are last names of people. The Kgd model assumes that the fracture has a cross section, which is a rectangular shape. And as it goes to the tip of the fracture, now the shape is something like this. Oh, that's my 3D drawing here is terrible. It's like this. Again, to propagate this fracture, to predict what is the width at the wellbore, to predict what is fracture half length, you can do the same thing that we did for the other one, and you can predict all of this. Something very particular about this model is that it predicts that net pressure decreases with time. And that's something that it doesn't really happen in the field except at the beginning when the fracture starts to propagate. But it doesn't happen in long fractures. Usually in long fractures, the pressure will stay more or less constant or it will increase. That's an important limitation of this model. And because of this model is used for relatively short fractures, where the fracture half length is smaller than the fracture height. And that could be useful for applications in which you need very short fractures, for example, frac pack completions, or for example, when you're trying to model a leak-off test with a relatively short fracture, this model it's also useful for that. And the last model is the radial model, in which now the fracture, if we had a wellbore, and let's assume that we are under conditions of reverse faulting, the fracture would propagate equally in the two directions in the horizontal plane. So the fracture is going to look like an ellipsoid, a planar ellipsoid, where the width now is going to be here at the center. Or the width of the wellbore is going to be the width of the center. And again, you assume the geometry, you solve the equations for fluid flow within a fracture, and again, you can predict what are all of these values. Let me ask you a question. There is something that we didn't use here that we just used before. Did you notice what that is? I'm going to write some things here just for the sake of completeness, but think about that. There's something that we didn't use. And if you give me that, I'll give you some extra points. Thanksgiving extra points. I count 3. What are we missing? Or what we didn't use? Please raise your hand if you want to participate. So we use equations in order to predict the width of the fracture. We use equations, look at the viscosity here. We use equations to tell what is the pressure gradient needed for the fluid to go from here to here. Oh, another assumption I forgot is that net pressure at the tip is equal to 0. Anyone notices what are we missing? I'm going to give you a little bit of help. What did we say about fracture length? What happens when the fracture is too long? What do we disregard with when the fracture is too long? What? No, friction is very important. Mr. Arakia, no. Mr. Kim. No. Remember this? We disregard toughness. So in all of these models, we consider that the toughness of the rock is equal to 0. It's not in the model. Look at the equations. It's not in there. All right, guys. We're on time. We'll finish here and continue next week. There is no lecture on Wednesday. Have you all happy Thanksgiving. I'll see you next week.